today?
Totally awesome, sir!
Alright, that's what I like to hear. Today's lesson is all about the question, what's the matter? I'm sorry, wrong question. The real question is, what is the matter, ladies and gentlemen? Okay. So, it's been an age-old question. What is this stuff all around us? What is this material? It starts with the ancient Greeks, where there were 2 points of view. Some of them said, if you take a piece of matter, say a sheet of paper, if you cut this piece of matter in half, and then took that half and cut it in half, and then took that half and cut it in half, and took that half and cut it in half, and took that half and cut it in half, and took that half and cut it in half. Eventually, if you had a precise enough knife, eventually, this group of scientists felt, you would finally cut it in half until you get to an indestructible, indivisible little nugget that wasn't made up of anything smaller. You would eventually get to a small little nugget that was not made up of anything smaller. It's called a fundamental particle. The Greeks called it the atom, meaning not dividable. Then there was another group of scientists who said, hey, I don't think so. I think if you have a piece of matter, and if you cut it in half, and then they take that half and cut it in half again, you take that, cut it in half again, cut it in half again, no matter how many times you do that, if you had a fine enough knife, if you had a small enough instrument, whatever little piece you had left, you'll always be able to cut it into 2 smaller pieces. It's like continuous. Now, they didn't do any experimentation. It was almost like a thought experiment. One group said, made up of these small little nuggets called atoms. The other group said, continuous. Can be sliced infinitely small as long as you have the equipment. Years later, our good friend Rutherford collected the first physical data that supported atomic theory. Genius. He shot those alpha particles through the gold foil, and he determined that the gold foil was made up of little tiny nuggets. He had the first evidence for the atom. I found the atom. There was dancing in the streets. The question was finally answered. We found the smallest little particle ever, not made up of anything smaller. We found the Greek atom. Unfortunately, the celebration didn't last long because other experimenters like J.J. Thomas discovered Thomson discovered that there was even smaller particles like the electron. So it turns out that the atom wasn't a Greek atom after all. It was made up of 3 smaller particles. They're called subatomic particles. Next level down. What am I talking about? Do you know, Dan? Where are they? That's what I'm talking about. Protons, neutrons, and electrons. The proton, the neutron, and electron were discovered, identified, isolated, physical data supporting it. Woohoo! Again, party in the streets. Yes?
There's just excuses at parties.
We found the smallest little nuggets that make up everything in the universe. The proton, the neutron, and electron. Turns out that there's not one little Greek atom, there's 3 of them. But the party, again, didn't last all that long. Because, ladies and gentlemen, a while later, it was discovered that 2 out of these 3 were made out of even smaller little nuggets. Wait. Ladies and gentlemen, the protons and the neutrons are actually made up of smaller little nuggets called quarks.
You believe that?
The electron, to this day, is still thought to be a Greek atom, a fundamental particle not made up of anything smaller. But protons and neutrons are made up of even smaller particles called quarks. And scientists today, in the year 2011, believe wholeheartedly that these quarks are Greek atoms. They are the end of the line. They are not made up of anything smaller. One of the reasons why they're so sure is because these quarks behave as if they're mathematical points. Think about that, folks. A mathematical point is kind of like an idea. You know what I mean? But these particles in experiments behave as if they're mathematical points. In other words, they don't have a little diameter. So if they don't have a little diameter, how could you cut them in half and go smaller? They behave like mathematical points. Now, I know what you're saying. How were these quarks discovered? How did they take the protons and the neutrons and determine that they were made up of even smaller little particles called quarks? See your hand over here. Cindy. Oh, no, the things that they are made up of, the quarks, they have mass. But they behave as if they're mathematical points.
But if you don't have a mathematical point is something like a mathematical point is like an exact value, and any number is an estimate. Like any number, numbers are infinite. Any number is an estimate. There's no such thing as an exact value. Am I wrong? Is that kind of like it? Like if you say 2, that just means it's not 1 and it's not 3. Like if you're using whole numbers.
Hey! Yeah, Rita, come on in.
Was Berkeley in the class too?
No, I had my college meeting, thank you very much.
Now, ladies and gentlemen.
Right there.
No.
Yes, he was.
These particles behave as if they're mathematical points, but yet they still have mass. I have a hard time with this too because, you know, a mathematical point is kind of like an abstract. It's like, it's not something physical, but, you know, this is something I still grapple with too. But we're going to leave that for now. And let's talk about where does this evidence come from? Well, throughout the world, the biggest one is in Switzerland and France. There are underground tracks,
Large
particle accelerators,
large hadron,
that use magnets to get charged particles to go faster and faster and faster and faster through these underground tracks. Some of them are linear tracks, where it's like a drag race, and the particle just goes faster, 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 faster. Other ones, like the one in France and Switzerland, is a big, huge, like 10 miles in diameter, underground racetrack where the charged particles, using magnets, go faster and faster and faster and faster, and the magnets keep putting a force on them, and we know that magnetism, the magnetic force can be exerted on moving charged particles. They go nearly the speed of light. And when they get these charged particles going so fast, then there's a person who has like this big switch, and basically they switch the track so that the particles stop going around in the circle, and now they go straight over here into this building where there are other particles just like hanging out, you know, having lunch. Hey, you know, what's going on over there? You know, and they're just like, and next thing you know, they're because these other particles come flying in and they smash in to these other particles hanging out. And when this collision occurs, debris goes flying everywhere. And in this building, which is like a 5-story building, there's layer upon layer upon layer of detectors, and they detect the debris, the stuff that comes flying off the collision between the charged particle that was made to go so fast and the particles that were just hanging out right here.
Distress.
Yes.
If they like, you have like they need to get it to the speed. Isn't that what they're trying to do? They need to get it to the speed of light. Like,
Well, it's impossible to get it to the speed of light.
well, here's my question. If you
And that's a relativity thing which we'll be learning about
if
shortly.
you could get someone with the speed of light, like I'm saying, if you get someone close, and then you take some, like it's like a momentum problem that I'm thinking of, like, and use something else close to the speed of light, and you put them in opposite directions, like wouldn't the sum of the velocities be greater than the speed of light, just momentum-wise?
I don't think so.
Because I'm thinking like
No,
let's say,
one's a
like
really
if you hit a brick wall at 10 miles an hour versus that's a 10 mile an hour collision. If you hit another car moving 10 miles an hour, right, it's like a 20 mile an hour collision into a wall. You know what I'm saying?
True.
So if you're moving half the speed of light, and then you hit something else going half the speed of light in the opposite direction, isn't that like hitting a wall at the speed of light?
No, because you're gain mass and you're less.
Oh, right.
It's like impossible.
We're getting into the realm of relativity, and I want to hold off on those questions until we study that, okay? Question?
Like, with the particle accelerator, how do they use, I get there are detectors, but how do they use the electron and the particle? How do they know what they're detecting? You know what I mean?
Well, there's different types of detectors, okay? One type of detector, imagine having a gas tube, and basically if a charged particle from the debris goes flying and goes through that glass tube, in the glass tube, let's say there's a hydrogen gas, yes? Well, that charged particle might collide into an electron and make that electron jump up a few levels. And then when that electron drops back down, what will it give off? Light. Okay? And by seeing the light that it was giving off, they can learn about how much energy the original particle had that bumped into the electron that made it jump up in the first place. So there's like indirect measuring devices. They can't see directly, but there's different various ways of, making indirect measurements.
And also, just out of curiosity, how many times do they perform this experiment? Do they do it every day?
Oh, yeah, every day. It's going on right now. Every single day. And if you're a renowned physicist, you have to make a proposal to say, hey, can I use your,
Large Hadron Collider.
multi-million-dollar machine to do my experiment?
Multi-billion.
Probably.
Wait, but can we, are tourists allowed in and go see it?
Pardon?
Are tourists allowed in to see it?
Yes.
Oh, I will.
Wait, now, have you seen Angels and Demons?
I've read it.
Well, I saw the movie. How, the guy steals, the matter from the Hadron Collider.
Right.
And, that would, bring the end to the, aren't there, people that say, once they finally get that going, the speed of light, it'll, end the world? They'll, make a black hole or something.
There are some fears which we're very nervous because the latest particle accelerator was so fast, they thought that the particle would go in and hit another particle, and basically there would be such an impact that the mass might be so dense that it might create some sort of black hole, and then the whole Earth would be sucked into the whole,
That's the way to go, though.
Okay. But that did not happen, and there's no reason to believe that would happen.
Maybe a quick death.
Now,
when you get anything.
How do you know you died?
in these particle accelerators, not only has the quarks that make up protons and neutrons been found, but other particles have been found. Particles that normally aren't seen in the regular universe. But they're definitely there. They're usually very short-lived. They're unstable. They exist as one little particle and then they turn into something else. But nonetheless, there's this whole collection of different particles that have been discovered in these atom smashers. So, just like the periodic table is a way to kind of make a chart to show all the kind of atoms, yes? Well, we have a couple tables to learn about today that give us a picture of the classification of all these little particles found in the Atom Smashers. And it basically starts off with all of matter. And basically, all of matter can be put into two main categories. As you can see, you have the hadrons, and the leptons. Now, the leptons are all fundamental. They're not made up of anything smaller. They're Greek atoms. They're the smallest of the small little nuggets that are not made up of anything smaller. They're indestructible, indivisible little nuggets that are the end of the line. So you might want to write on your chart that, these leptons right here are fundamental.
What if you got hit by one of those, little, not you personally, if anyone got hit by, one of those little charged parts,
Well, as we're going to see, some of these little leptons are going through us constantly, all the time, even right now.
So,
fundamental, not made up of anything smaller. And if you look on the next chart over, there turns out to be 6 different of these leptons. And you probably recognize the first of them is the good old electron. The electron is a lepton. It's not made up of anything smaller. So we have the electron has a charge of -1 e. It's a Greek atom. It's a fundamental particle. Now, much more difficult to find is the electron neutrino. It's another lepton. And again, I'm just drawing this symbol there. The symbol called nu. It's a Greek, italic looking V. And one of the reasons why it was so difficult to find, gentlemen, is because they're neutral and they have very, very small amount of mass. And there was great debate for years whether or not they even existed. And I believe it was the Japanese who first actually detected them in these underground water tanks. And basically, if the electron neutrino goes through and collides with something, once again, it might excite an electron, which ultimately will give off light. And they actually had verifiable proof for the electron neutrino. These two here that I have shown are very abundant in the universe. And they can be detected inside and outside of the atom smashers. These next 4, though, are more exotic. They have only been discovered and only been observed inside the atom smashers. We have the muon, symbol mu, same charge, -1 eV, and we have the muon neutrino. And we have the tau, and the tau neutrino. Oops.
Is that the same symbol as quark?
Yes. So again, these over here, very abundant, found in the universe. The other 4, kind of rare, only been observed in the particle accelerators.
So they're all in atom smashers?
They have all been discovered, of course, in atom smashers. Okay? But these 2 over here, all the way to the left, have been found out in the universe, not in atom smashers. Now, going back to the other major classification, the hadrons themselves are not fundamental. If you're a particle and you're a hadron, you're made up of smaller particles. So the thing you need to maybe make a little note about the hadrons are made up of quarks. They're like a little conglomerate, a little cluster of quarks. And again, in these atom smashers, there have been 6 different quarks discovered. And let me write up these quarks, and then we'll take a quick break. Okay, so we have the following quarks. We have the up, and the down, the charmed, and the strange, the top, and the bottom. So I'll write out this information, and then when you come back from your break, we'll continue with our discussion.
Pretty cool. Cool like a gang, though, short.
You should all chase you down the hallway with the
Yeah.
That would be so fun.
There have been 6 quarks discovered.
Clap.
Hey! Oh!
Hey!
Risa!
Is Brett really that one?
Ladies and gentlemen, 6 different quarks.
I did, actually.
Live.
Now, it turns out that these quarks are never, ever singled out by themselves. You can never just have one of these quarks by itself. Not that we don't like. It's not like we don't think it's because we don't have the technology to do it. We believe that like it's a law of nature. You cannot have one of these quarks all by its lonesome hanging out. It's always found as either a cluster of 2 or a cluster of 3. So let's go back to the classification of all matter. There's the leptons. They're not made up of anything smaller. And the hadrons. The hadrons are made up of clusters of quarks. And these hadrons get classified into 2 smaller groups. The baryons, Mike, and the mesons.
Yep.
What's the law called? Law.
Again, I don't even know if they talk about it as a law. That was actually my language there. But the quarks are believed to be always found in either a cluster of 2 or a cluster of 3. So the baryons are the threesomes. Okay? If you have 3 quarks clustered together, it's an example of a baryon. Now there's 2 very important baryons that you guys need to know about. And basically, one of them is the up-down baryon, and the other one is the down-down-up baryon. And it doesn't matter which order you write them. So in other words, I could have written the top one as a down-up-up, and I could have written the next one as a down-up-down. Those are one and the same, ladies and gentlemen.
I get married? I do.
But these are very important baryons. Anyone want to take a guess what these 2 suckers are? Yeah, one of them is the proton and one of them is the neutron. The proton and neutron were made up of quarks, yes? And you either have to memorize which one is which, or there is a way to figure out which one is which. Can anyone?
I know.
Yes, Diana.
You take, there's numbers plus 2 over 3, and you just add those. If it's UUD, then just add 2 over 3 2 times, and then the negative.
Yeah, what is that negative 1/3 E and the positive 2/3 E? That's the what of the particle?
The elementary.
Yeah, I'm looking for a key word that starts with a CH. That's the charge of the particle, yes? So by considering the charge of the particle, we can identify which one is which. Because if it's a proton, what should its elementary charge come out to be, Diana? Exactly. And do you need, if it's a neutron? 0. So let's go back over here. Okay. Two important examples of baryons. The up, up, down. The down, down, up. If you look at their charge, what is the up? Positive 2/3 E. And another up, so plus another positive 2/3 E. All right, gentlemen, I don't want you to hear chatting there. plus a down negative 1/3 E. And if you add them up, what do you get? Jacques? So guess what the up, up, down turns out to be for Jacques? The proton. And if you look at the down, down, up, you have negative 1/3 E plus negative 1/3 E plus positive 2/3 E. And Justin, what does that add up to?
I'm going to go with 0.
Therefore, guess what the down, down, up is actually?
A neutron.
So, once again, ladies and gentlemen, as we saw with the leptons, the same holds true with the quarks. You see these guys over here? They're the most abundantly found inside and outside of the atom smashers. These over here have only been observed from the debris from the atom smashers. Now, there's many, many different baryons. For example, I could take a charmed, a bottom, and a down, cluster them together. I have an example of a baryon. That particular baryon also has its own name. Okay? And then there's the down charmed strange. That's another baryon. There are so many of these baryons that, a famous physicist once said, if you expected me to memorize all this stuff like this, I would have gone into biology. They're like, physics, we're not supposed to be doing all this classification and remembering of names and all.
What are all the formulas? Reconciliation.
That's true. So, again, there's all these different types of particles. So, you might think, there it is. The ancient Greeks thought that there was a single fundamental particle, Hannah? And that, okay. And that everything was built upon it? Well, you might think, there they are, right there. 6 quarks, 6 leptons, not made up of anything smaller. Total of 12 fundamental particles. But unfortunately, ladies and gentlemen, that is not the end of the story.
What?
It turns out that each one of these quarks and each one of these leptons has an evil twin brother.
Like the equilibrium forces your book.
That's not evil.
Identical twin, but the opposite charge. And also, sometimes a little bit different spin. But the main thing, the opposite charge. So, ladies and gentlemen, there's not just 6 quarks and 6 leptons. There are these evil twin brothers, and they're called antiparticles. There are 6 antiquarks and 6 anti-leptons. Dun dun dun.
No, it's dun dun dun.
Whoopsie.
And when we're like Windows locks on, that's your text.
Here's the anti-up. how is the anti indicated? By a little line above the up. You see the little tiny line above the up? You know you're not talking about the regular up. You're talking about the up's evil twin brother. The anti-up. If the up has a charge of positive 2/3 E, what is going to be the charge of the anti-up? And then we have the anti-down. And then we have the anti-charmed. And then we have the anti-strange. And the anti-top.
Sideways. Swivel clockwise.
And the anti-bottom.
What?
Same thing with the leptons. Each of the leptons has an evil twin brother. The anti-leptons.
Where are they? They're stagnant.
They like veal? I mean, like, they just eat it running?
You really think you're gonna?
Ladies and gentlemen, I hear awesome questions out there. Number one, they're only found in the atom smashers. They're very short-lived.
Even the anti-up and the anti-down.
And basically, ladies and gentlemen, one of the resounding questions these particle physicists have is when the universe was formed, there was probably the same amount of matter and antimatter. And where's all the antimatter? Where, how come, there's not around? So basically, we have the anti-electron. And what's the charge of the anti-electron? Now, this antiparticle happens to have an alternate name, and you're responsible for knowing that eternal alternate name. Does anyone know what the anti-electron is also called? It's called a positron. So you might want to make a little note here. This one right here.
You know that? I said it.
Now, sometimes people get confused and they think the positron is the same as a proton because they both have a charge of positive 1 elementary charge. But that's not the case. The positron is fundamental. It's not made up of anything smaller. The proton, on the other hand, is what? An up-up-down cluster together. Like 2,000 times more massive. So they both have the same charge, but a proton and a positron are not the same thing. Another thing that I find absolutely fascinating is you might have heard of a medical test called a PET scan. Well, PET scans, I believe it stands for positron emission testing. They actually shine positrons into the human body, okay, and basically when they interact with the electrons, they give off light energy, which can be used to form images inside the body.
Is there like an advantage to it?
I guess you can see things you wouldn't be able to see with other means. Okay? So that brings me to another interesting point, but let me finish writing these out, and then we haven't talked about what happens when matter meets up with antimatter. What happens when a particle meets up with its very own evil twin brother? So down here we have the
There's a fight of the way.
anti-neutrino. And we have the muon, anti-muon, anti-muon neutrino, anti-tau. Ladies and gentlemen, if a particle comes in contact with its own evil twin brother, its own antiparticle, whoosh! Total annihilation. They turn into pure energy. Now, remember, ladies and gentlemen, Einstein showed that energy and matter are two forms of the same thing, and a tiny little piece of matter gets turned into a huge amount of energy. Like, you multiply by the speed of light, which is a big number to begin with, squared. So a tiny little, piece of matter is equivalent to a massive amount of energy. Well, if a particle meets up with its antiparticle, whoosh, turns into pure energy.
What is energy?
Well, you can think of it as light energy. So it turns into light, photons.
Is there a force? Is it like an explosion? Is it like?
So is that like the Big Bang?
That's what the basis of that movie, Angels and Demons.
Right.
They had a vial of antimatter. It was being held in place by a magnetic field, but if it was ever exposed to regular matter, release a massive amounts of energy. Huge, bomb-like explosion. So, ladies and gentlemen, we have to go all the way back to our classification, and we never spoke about what the mesons are, the mesons. Okay, basically the mesons are another type of hadron, but it's not a cluster of three. It's one quark and one antiquark matched together. So, for example, if you had a down and an anti-charmed, and this could be like a typical Regents question, a down and an anti-charmed, and they'll say, what kind of particle is that? Well, you'd have to recognize that's a meson. Or what else could that be called, really? A broader category. A hadron.
Or you could just answer everything as matter.
Yeah, usually it's multiple choice though, so you're given choices. So what I want to do at this time, folks, is show you a little video of the CERN, that atom smasher in Switzerland and France.
It's a little thing.